Okay. So, if I do this in 2D, so for this do not worry about staggered grid. Actually Poisson solver Rishabh has done it by some very sophisticated scheme called multi-grid scheme. So, I think you are going to give us the one package. So, you can use his package. So, you do not need to worry about Poisson solver, it will give you the correct value. So, we will try to make this package bit user friendly, so you can use it. Now, but so the scheme I am telling you is simpler than he is using multi-grid, but we are going to use one of the simpler ones in this slide. So, first thing is how does the equation look like? So, is it, I hope it is visible at the back as well. Okay. So, this is the x derivative, double x derivative, this is double y derivative, plug it in, you will get this equation. If I make hx equal to hy, then I get this equation. Okay. Now, this you may recall is one of the properties, it comes from a properties of a Laplace equation, that value of the function at any point is equal to the average of its neighbors. Okay, that is the property of Laplace equation, it is just that. Now, if you want to solve it, there are many equations. How many equations are there? For every ij I have an equation. So, I have n squared equations. So, you write it in terms of matrix, and how does the matrix look like? Now, you have to first set it up some convention. So, this matrix look, so first you have to set it up 5 0 0, 5 0 1, 5 0 2, 5 1 0 like this. So, this is my vector unknown. Now, matrix equal to 0. So, let us look at phi ij. So, it involves phi I plus 1, same j, but there are two of them, I minus 1 j and I plus 1 j. So, this has factor minus 4, right. Ij will have minus 4, it should be there minus 4, and other ones are 1 and 1. So, the neighbor is, this corresponds to I minus 1, right, because you see there is a phi ij, phi I plus 1 j, phi I minus 1 j. Okay, people sitting in the back should come in front. I have so much, but so this I minus 1 j will be here. So, this is 1 and this is 1. So, the entries are minus 4 1 1 branded, but there are two more entries. What are they? Is going to be phi I j plus 1 somewhere down the line, which will be somewhere here. There is another line, is one sitting here, and another line one sitting here. So, there are 5 lines, center line is minus 4 and there are ones like that. Okay. Now, you need to solve this equation. Now, there is a way to solve it, but is clumsy. Right now, I have not done it, but it is definitely clumsy, but there is a simpler way. Okay. You can, well, I have not done the matrix solvers, but you can solve it, and there is a way to do it. Hopefully, we will have time to do this, but I will show you another way. It is called iterative procedure. So, I do not know the correct value. So, you start with initial condition, and by the way, this is called boundary value problem really. So, given the boundary condition, I can solve for phi ij everywhere, but my boundary must be fixed. I should not change my boundary. So, in this problem, you have to, whatever boundary is given, you should give me the values here. The two types of boundary condition, one is Dirichlet, which is value of phi, another one is Neumann, where you set the derivative, you set the derivatives to some value. So, once you set it up, then you compute iteratively, and of course, you put the initial condition. So, these are fixed, but in between I start with some initial guess. Initial guess, it may be wrong, no problem, and then iterate it. So, every phi ij I will compute using this. Okay. So, you start with wrong values, but you will quickly converge. So, these values are fixed here, 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 here. But then for any ij, I am going to iterate by this procedure. So, just make a loop for I going from 0 to n minus 1, j going from 0 to n minus 1, I compute this every point. And you will converge reasonably quickly, it does not take too long, and you converge to the right answer. It is stably, it just goes to the right convergence, because Laplace equation has a solution that has a property, this property, it will converge. Now, this is called Jacobi method, but you want to make it faster, sometimes it can take long time. You can apply this scheme where you put a variable omega which is positive, but order unity 0.4, 0.3. Okay. So, I just changed it by this 1 minus omega by 4 and omega minus. So, this is a new term which has been added. This is called relaxation. So, these are, I mean, this is why trial and error with some mathematics, but you will discover that this will work better. There is yet another way, that right now I have to use two arrays. One is a new array, right. I mean, when we think that I should not, I have previous value, I compute the new values by this, then make that as a current value. You understand? I mean, I have present value, I compute the new value, but after the new value, for the next iteration, the new value becomes the current value. But Gauss and another mathematician, Seidel says, well, do not do that. If you keep changing by in the loop, so do not make a new array, on the same array keep changing it. It looks scary, but it works faster. This is called Gauss-Seidel method. So, you just replace in the loop phi ij by this, just replace, this left arrow means replace. So, in the use only one array and just keep replacing, it works faster. In fact, it is better scheme. So, the previous two schemes can be replaced by these schemes where you just keep replacing when you are in a loop. Now, this for Laplace equation, in fact, similar schemes works for Poisson solver. Poisson solver I have to do Laplacian f equal to Laplacian phi equal to f. So, right hand side is ij, I will assume that h is equal, okay, both hx equal to hy. So, this equation. Now, I apply the same idea, phi ij is this. I just rewrite what is phi ij and iterate it. If you iterate it, you will converge, but it takes a bit of long time, but you can converge. Okay. So, this is in fact, this is a Jacobi method. Okay. Now, you can make it more sophisticated by again the four trials, use omega, which this is called over relaxation. You are relaxing, you are not relaxing the same way, but you over relax, you put more omega, omega not equal to 0, or you can use that left arrow, you keep replacing. By the way, f is given. So, Poisson solver, you give the boundary condition as well as f at every point. F is there, the source is everywhere. So, this comes in electrodynamics, electrostatics. So, this is potential, but you have to give me charge everywhere. Okay. So, these are the schemes for Poisson solver and Laplace solvers. Okay. I have not shown you any code, but I hope you are writing the code. Okay. So, maybe I will show you one example in the next class.